So welcome to my lecture series. So now we discuss applications of superconductor. So in that applications we discuss superconducting quantum interference device SQUID. So the superconducting quantum interference device is a very sensitive magnetometer used to measure extremely weak magnetic field based on superconducting loops containing Josephson junctions. So SQADs are sensitive enough to measure fields as low as 5 into 10 power minus 14 Tesla. So with a few days averaged measurements. So their noise levels are low as 3 feet Hertz power 1 by 2. So for comparisons, as a typical refrigerator magnet produces 0.01 Tesla. So and some process and animals produce a very small magnetic fields between 10 power minus 9 Tesla to 10 power minus 6 Tesla. And so there are two main types of SQID, direct current and radio frequency. So direct current DC and radio frequency RF. So RF SQID can work with only on Josephson junctions, and which might make the cheaper to produce but or less sensitive. And this is that DC SQID. The DC SQID was invented in 1964 by Robert Jackliffe and Siller of Josephson effect, postulated at the Josephson effect and parallel in a superconducting loop. It based on the DC Josephson effect. In the absence of any external magnetic field, the input current I split into the two branches equally. So if a small external magnetic field is applied to the superconducting loop, a screening current IG begins the circulate the loop that generate the magnetic field, cancelling the applied external flux. So and creates an additional Josephson phase which is proportional to its external magnetic flux. So the induced current is in the same direction as I in one of the branches of superconducting loop and is opposite to I in the other branch. So the total current becomes I by 2 plus Ig in one branch I by 2 minus Ig. So the options size and coupling with the environment. So the photons, nuclear spins, ions, semiconductor spins, quantum dots, superconducting circuits, and superconducting circuits, strong coupling to environment and short coherence times, and strong SQID coupling fast gates. And these circuits are easy electrical access and easily engineered with capacitors, inductors or Josephson junctions, easy to fabricate and integrate. And so the materials used traditional superconducting materials for SQIDs are pure neodymium or lead alloy with a 10% of gold or indium. As pure lead is unstable when its temperature is rapidly change. To maintain the superconductivity, the entire device needs to operate within the few degrees of absolute zero, so cooled with the liquid helium. And quantum characteristics, how can macroscopic device exhibit quantum properties? So LC oscillator circuits like quantum harmonic oscillator, so we can use that characteristics. And Cooper pair box, so based to compact continuous charge QR, and Cooper pairs are trapped in box between capacitor and Josephson junction. So charge in the box correlates to energy states. And interaction, so easily fabricate transmission lines and inductors to couple circuits, so can be coupled at macroscopic distances. And then fabrication, So use exciting microfabrications techniques from IC industry. So electron beam lithography for charge and flex SQIDs. So optical lithography for phase SQIDs. In a future, the active area of research and need to simultaneously optimize the parameters, new materials to improve properties, engineering better circuits to handle the noise, so local RF pulsing. Thank you. See you in next video.